Good evening. I'm Spot On Weather meteorologist Matthew Euler, and welcome to my latest video. And tonight we're going to talk about a continuation of the El Nino topic. We're going to delve into El Nino and U.S. snowfall. Here's a nice picture on a winter's day of a snow-covered road. Wherever this is, I don't have the exact location, but this is just one of those really nice winter scenes if you really like the winter wonderland theme, and really enjoy the snow. So let's go ahead and jump right into it. I'm first going to start off tonight's video by talking about typical El Nino winter characteristics. All right. Again, one of the main motivators for doing these El Nino videos is because of the upcoming forecast for a fairly strong El Nino to occur. Many of the models are indicating a El Nino conditions coming on in between the May and July 2023 time period. And, by the time we get to the fall and early winter, we could be seeing a fairly strong El Nino. And I'm going to break down what that exactly means as far as the weather across the United States, specifically the snowfall. First, let's start off and talk about these El Nino winter characteristics. What you typically see during the El Nino winter is an active southern branch jet stream, otherwise known as a subtropical jet. This increases the amount of low-level moisture for storm systems to work with. So we get a lot of moisture with the southern branch of the jet stream. Storm track is going to pretty much be right along that more active jet stream further south, stretching from Southern California right along the Gulf Coast of the United States. What this means is that locations to the north of this predominant storm track will see colder temperatures, typically below normal readings, and that is more in line of favoring wintry precipitation, or at least there's a better shot of wintry precipitation for many in the El Nino winter further south. Meanwhile, the other ingredient you have during El Nino winters is the polar front jet stream is going to dip down from central Canada right into the mid-Atlantic and New England. Now, the timing would be critical, as it always is each winter. With storm systems, you want the colder air plus the moisture at the same time. Preferably, you want that warmer, moist air to overrun colder air at the surface, and that precip is then going to fall into the colder air at the surface. Now, one thing I want to caution everybody about is not all El Nino episodes are exactly identical. For example, the strength of El Nino episodes varies from winter to winter, and also there's different climate drivers or teleconnections that can play into the overall outcome. I'm mainly focused today on El Nino characteristics, the type of weather we would see during the winter season. I'm also going to talk a little bit about one other climate driver or teleconnection known as the North Atlantic Oscillation. Let's continue. I wanted to show you how things pan out as far as the Pacific Ocean pressure patterns and kind of compare El Nino versus La Nina. The graphic here on the left, the SOI stands for Southern Oscillation Index. Now, this is the pressure pattern. Generally, we compare 2 points in the Pacific Ocean for the Southern Oscillation Index, the pressure patterns, generally from Tahiti right west to Darwin, Australia. So between Tahiti and Darwin are the main 2 points that are chosen across the equatorial areas of the Pacific Ocean. And generally, wherever you see this red coloring, that indicates above normal pressure in millibars. Where you see the darker gray and the blacks, that indicates below normal barometric pressure in millibars. And this right here is December, the months of December and January. These 2 images represent those 2 months. So in general, what we have, the top graphic here on the upper left for the SOI pressure pattern shows a positive situation, positive SOI, positive condition in which we have a La Nina, where we have higher pressure over Tahiti, we have lower pressure over Darwin, Australia. All right, so the air is going to flow from higher toward lower pressure from Tahiti right west to Darwin in this case. Bottom left image here shows the opposite effect. Now, this is associated with a negative SOI This is associated with El Nino conditions. And now the pattern has just flip-flopped, the pressure pattern here. We now have higher pressure over Tahiti during El Nino winters, and we have lower pressure over Darwin, Australia. And again, the air is going to generally flow from high toward lower pressure. In this case, the pressure gradient would direct the air from Darwin towards Tahiti. So that's the big difference here, where the highest pressures, the above normal pressures set up at the surface, and where the below normal pressure set up at the surface. And what's calculated is the Southern Oscillation Index. If we look at the graphic here on the right, showing you the top right, upper right here picture depicts El Nino conditions. The black L represents areas of lower barometric pressure. The black H represents areas of higher barometric pressure. And it kind of goes in line with what you see down here in the bottom left. When we look at the negative SOI or the El Nino conditions down here with the pressure patterns, notice, like I explained down here in the bottom left, when we're looking at the SOI index, notice where the high pressure sets up in an El Nino. It's typically over the western portions of the Pacific Ocean, closer to the maritime continent of Australia, closer to Darwin, whereas you have lower pressures in the eastern Pacific during El Nino. And what these different color schemes indicate, this orange, these dark oranges and stuff beneath the low pressure area, this represents areas of above normal water temperatures associated with El Nino. That's what these represent. And then bottom right here, we see now a flip in the pressure pattern. So during La Nina, which we just came out of 3 consecutive winters of La Nina conditions, we now have higher pressure situated over Tahiti, over the east and central Pacific, and we have lower pressure over the area near Darwin, Australia. And so I just wanted to show you, look at the cooler than normal waters during La Nina across the same areas that were warmer than normal here in the upper right during El Nino. So it's just a matter of looking at the pressure patterns, the underlying water surface and where these sea surface temperature anomalies are occurring. Typically lower pressure occurs, rising air motion, and low pressure occurs above warmer than normal water, and high pressure occurs at the surface, generally over colder than normal waters. You have sinking air motion. Now, let's take a look at the ENSO tropical rainfall patterns. Now, this is wintertime tropical rainfall in inches. So you see the scales at the bottom of each of these images, just generally showing you the difference between a strong El Nino and where the wettest and driest conditions set up, and then a strong La Nina here on the right, similar situation here. Now, some of the key takeaways for strong El Ninos during the winter months is we see tropical convection and the jet stream extending across the central and eastern Pacific, represented by this red arrow. And typically during strong El Ninos, this type of setup where we have wetter than normal conditions in the eastern equatorial Pacific and drier than normal conditions in the western equatorial Pacific, what that normally sets up is a positive PNA pattern, a positive Pacific North American pattern where we have an upper level ridge along the west coast of North America when we have the wetter conditions beneath it here over the eastern and central portions of the equatorial Pacific. We look at La Nina here on the right, we have the opposite effect. We have drier than normal conditions now from the west coast of Peru, extending westward into the central equatorial Pacific during La Nina, and then we have wetter than normal conditions in La Nina out in the western Pacific along the equator. And what happens in strong La Ninas is the tropical convection and the jet stream are confined more to the western Pacific during La Ninas. Notice the jet stream here in strong El Ninos. That jet stream extends all the way across the Pacific right on into Southern California. And the other big point here to make is with strong La Ninas, we typically have a negative PNA pattern, and we really saw this represented well this past winter season when we had a persistent upper level trough parked along the western portions of North America. Moving ahead now to what a typical El Nino pattern looks like, in addition to the pressure patterns in the Pacific, what those rainfall patterns look like in the Pacific. This is that extended jet stream here, this big red arrow, and it's much further south. Look at the green coloring here. Wetter than normal wintertime weather for Southern California, Southern Arizona, Southern New Mexico, Texas, parts of Louisiana and the Gulf Coast right into Florida, and right up the eastern seaboard a little bit towards the mid-Atlantic. We typically see a polar front jet stream coming down from Canada heading towards New England and northern mid-Atlantic. If we get the merger of this moisture, the wetter than normal conditions associated with the storm track and this subtropical jet in combination with the colder air coming down from the north with the polar front jet stream, we typically see quite a bit of wintry type precip occurring up into the mid-Atlantic. Now we do see during El Nino patterns drier than normal conditions from Illinois, Indiana, Ohio, right down to West Virginia, portions of West Virginia, Kentucky, Tennessee, and northern Mississippi, Alabama, Georgia, back to Arkansas and Missouri, typically drier than normal winter weather. And then we see this warmer than normal pattern show up across Iowa, extending westward, southern Minnesota, Dakotas, Nebraska, all the way back to the Pacific Northwest and Western Canada during El Nino winters. And look where your low pressure system is situated as well, back to just to the south of the Aleutian Islands of Alaska and the Northeast Pacific. So what happens is this deep low pressure system, the lowering of heights, is going to pump up a downstream ridge across western North America associated with the positive Pacific North American pattern and a downstream trough into the New England states and parts of the Mid-Atlantic during El Nino patterns. One big thing to note is this El Nino pattern features this much more southern or suppressed storm track. You're not going to get as many cutters or inland cutters working their way up there along the spine of the Appalachians or even back further into the Midwest. Typically, you're going to get more of a southerly route of the storm system, leaving areas north of this main storm track in the colder air. Here is the 500 millibar ENSO pattern comparisons. Warm ENSO refers to El Nino, cold ENSO on the bottom refers to La Nina. Typically during El Nino, what we see is a deep upper level low at 500 millibars, situated generally to the south of the Aleutian Islands across the Northeast Pacific. And again, the main thing I want to get across here is this deep area of low pressure is going to allow for much lower than normal heights, which is then going to result in much higher than normal heights and a pumping up of this upper level ridge downstream over parts of western North America associated with that positive PNA pattern I mentioned. And then downstream of that, you're going to get troughing. Troughing, generally an El Nino pattern at 500 millibars, you're going to get lower than normal heights generally across the southern U.S. And then also extending slightly northeastward into the mid-Atlantic states. Notice this major feature here where my cursor's at. This is associated with anomalously high heights. Higher heights than normal at 500 millibars, 18,000 feet over Hudson Bay, Canada. So you got a blocking high to the north, and that's going to allow troughs and storm systems to move beneath to the south of this major blocking high over Hudson Bay in eastern Canada. That is the pattern for a much favorable situation for El Nino winters as far as wintry precipitation for parts of the southeast right into the mid-Atlantic. Bottom here, this graphic shows La Nina conditions during the winter, and now look at the pressure patterns have just flipped. We now have an extensive upper level high situated just into the Northeast Pacific, ridge axis extending north to the western Aleutians and the Bering Sea, and we actually just saw this textbook configuration to the upper air pattern the winter of 2022-23, this past winter. This upper level high just sat there for days, and when these heights rise, pump the ridge up out here over the western Aleutians to the Bering Sea. Downstream of that anomalously high height center, we're going to have troughing across the western portions of North America, including Canada, western Canada, into the western U.S. And then downstream of that, you're going to get ridging in the mid-Atlantic and southeast. What a textbook winter we just had showing this. But real interesting comparisons. El Nino at the top, La Nina at the bottom, and what a difference we have here. Let's look at the 500 millibar. Let's look at those anomalies, the height anomalies here for winters during El Ninos. And then at the bottom right here, I'll get into the 2 meter temperature anomalies during El Nino winters. All right, so we look back at the ERA 5 reanalysis, ensemble mean, running from the months December through February, meteorological winter months for the years 83, 87, 92, 98, 2003, 2005, 2007, 2010, 2015, 16, and 2019. These were associated with El Nino winters. And what you'll notice here is this deep purple coloring here at 500 millibars across a good chunk of the central Pacific, north of the Hawaiian Islands, as well as into Northeast Pacific. This is associated with anomalously low heights in decameters. And again, you have a very deep trough. You got a closed upper level low situated in this location in the Pacific. You're going to lower heights here. You're going to cause the ridge downstream to build or amplify, resulting in this higher than normal heights across western portions of Canada, as well as into, with the blocking high here from the Atlantic side, higher than normal heights over the top across Canada during these particular winter El Ninos events. Okay, look at the lower than normal heights. Also, the green shading and this blue shading across Texas, Southern California, extending eastward, right along the Gulf Coast I-10 corridor, includes you in Florida, right up to the Mid-Atlantic. So you see where the lower than normal heights set up in all these previous El Nino winters. And then over here on the bottom right, we're showing you the same time periods, December through February, with the same years for El Nino. But now we're looking at monthly air temperatures anomalies at 2 meters. And wouldn't you know it, associated with upper level ridges, we have this maroon and red coloring indicating much above normal temperatures relative to average, going back to the 1991 to 2020 averages. And then the blue shading here in the southern U.S., showing even up to the mid-Atlantic and Florida, we have below normal temperatures relative to normal. Now, let's take a look at these graphics provided by NOAA. These are the El Nino temperature anomalies. Again, for those winter months, the meteorological winter months of December, January, and February, I'm showing anomalies here on the left. I'm showing frequency of occurrence composite here on the right. You'll see the scales beneath each of these graphics. So blue coloring here on the graphic on the left indicates below normal temperatures, generally where we'd expect them along the southern U.S. right up into the mid-Atlantic. And then over here on the right, we're showing the frequency of occurrence. Now, this is a percentage over here on the right, this composite frequency percentage. How often do we see below normal temperatures during El Nino winters? Taking all the El Nino winters combined to this point, the highest chance of below normal temperatures on the order of 70 to 80% in the bright orange here, right from New Orleans, Biloxi, Mobile, Pensacola, and also southern Florida. And then even pretty good high frequency or probability up to the mid-Atlantic, the Carolinas. There's a 60 to 70% chance you see below normal temperatures up to New England as well. 60 to 70% chance during El Nino winters for below normal temperatures. But you get the general idea here. This is a storm track along the southern route. This is where your thicker clouds are going to be during the winter season, and cooler temperatures are going to be the results. Now let's look at the El Nino precipitation anomalies. Same months, December, January, and February. Now these anomalies are in millimeters, so the scale down here, this is in millimeters, not inches. And then the frequency of occurrence is here on the right again. This is percentages, probability of percentages, okay? So anything green on this graphic on the left or blue indicates above normal precipitation during all the El Nino winters in the months of, well, it's covering December, January, February. Notice again where that green is along the southern U.S., right into the Florida. Gets a lot of rain during El Nino winters. And then also up into the mid-Atlantic, even going all the way up into the coastal sections of New England, including Boston. Notice there's a higher amount of precip here also in Northern California, Oregon, coastal Oregon, and Washington State associated with storm systems in general. What's the frequency occurrence of these values occurring? Drier than normal conditions is typical in the Ohio Valley, and it has some of the higher probabilities associated with it on the order of 70 to 80% in some of these areas. Additionally, we see drier than normal conditions across Montana, Idaho, Wyoming, into Utah and Colorado, and that has a fairly high probability of occurrence as well. Now, let's look at the El Nino snowfall anomalies for the same months. December, January, February. If you see blue coloring here on this graphic on the left, that indicates above normal snowfall. And by the way, this is in inches. So, for example, the dark blue here is 3 to 5 inches, up to 5 to 7 inches above normal for the season, generally from the mid-Atlantic right up to New England. And then we have below normal snowfall in El Nino winters across Wisconsin, Michigan, as well as Minnesota, Iowa, northern Illinois, back to the Dakotas, parts of the West, Intermountain West, Rocky Mountain states, as well as parts of Oregon and Washington state. We have above normal snowfall with those southern storm tracks into New Mexico, into North Texas. You have above normal snowfall. You have above normal snowfall in Oklahoma City, Little Rock, Memphis, right into Kentucky, So this is real interesting. This is the frequency or probability of occurrence, the frequency percentage, showing a pretty high correlation frequency here across the upper Midwest, Iowa, Wisconsin, Michigan, Minnesota, Dakotas, for below normal snowfall and El Nino winters. And then also pretty high confidence that we see above normal snowfall across parts of New England. And then, I'd say moderate probability, 40 to 50% across the Mid-Atlantic during El Nino winters. Now, if you look at a review of the El Nino years, this is broke down. There's 26 total El Nino years here for the winters. And there's different categories here: weak, moderate, strong, and very strong El Ninos. And generally, these are the intensity of the above normal water temperatures. We look at the Nino 3.4 region here in the central equatorial Pacific area. We see what those water temperatures are, how much above normal they are. If they exceed 0.5 degrees Celsius above normal in this Nino 3.4 region, then we have an El Nino. All right, so a weak El Nino in the Nino 3.4 region is on the order of 0.5 to 0.9 degrees Celsius above normal water temps. A moderate El Nino would be classified when the water temps here are 1 to 1.4 degrees Celsius above normal. When we have strong El Nino classification, we have water temperatures right in this Nino 3.4 region, 1.5 to 1.9 degrees Celsius above normal. And then very strong El Ninos are classified as water temperatures in this Nino 3.4 region exceeding 2 degrees Celsius. Now, look over here again on the left and notice out of the 26 cases, we've only seen 3 winters which have featured very strong El Ninos. We have seen 5 winters featuring strong El Ninos. We have seen 7 winter seasons that have featured moderate El Ninos, and then weak is the majority of the sample size. 11 of the 26 winters we saw weak El Nino conditions. All right, so we don't see very strong very often. We've seen it 3 times since the winter of 82-83. All right. Our most recent El Nino was a weak El Nino back in the winter of 2018-19 before we saw 3 consecutive winters of La Nina conditions. So now, we looked at just El Nino and the general characteristics of El Nino winters, but now let's tie in the North Atlantic Oscillation, the NAO, with El Nino, combine them. So in addition to El Nino alone, let's take a look at this NAO. Let's see how it plays a significant role in determining sensible weather during the winter season. And believe me, it does. I was doing some research on this and it was really interesting to look at. So here's we go. When we see an El Nino plus a negative NAO, we typically see colder and snowier conditions for many locations across the eastern U.S., including the Mid-Atlantic. That's an El Nino and a negative NAO. Negative NAO is going to be associated with the blocking ridge or blocking high at higher latitudes. Let me go back. It's going to be associated with this. Higher than normal heights at 500 millibars with the upper level ridge. Okay? To the north over Canada, over eastern Canada. All right? Now, when we get the combination of colder temps associated with a negative NAO, negative NAOs typically results in colder temperatures beneath that anomalously high height ridge to the north. Plus you get ample moisture from a stronger subtropical jet stream because of El Nino. Those two combined really do provide the necessary ingredients for above average snowfall. Now I took this quote here, the last bullet of this slide. In boreal winter, El Nino events tend to be associated with the negative phase of the NAO. That's important. I looked at the research that was conducted here titled Modulation of the El Nino Teleconnection to the North Atlantic by the tropical North Atlantic during boreal spring and summer. This was done by Castleman et al. In 2022, pretty recent. And they took a look at past El Nino events, and El Nino events, literally, this is the quote, El Nino events tend to be associated with a negative phase of the NAO. So we're saying that NAO, the high latitude blocking, is more favored in El Nino years, El Nino winters. Let's take a look at the NAO here as a review. The different phases include positive phase here on the left and a negative phase here on the right. And with a positive phase of the NAO, you get anomalously low 500 millibar heights to the southwest, just off the southwest coast of Iceland. You get higher than normal heights, 500 millibar heights, generally around the Azores area. So we have stronger than normal higher heights here, or higher than normal higher heights, lower than normal lower heights here. And what that does is the height gradient between a stronger upper high and a stronger upper low results in a faster zonal west to east jet stream across the North Atlantic. That results, the positive phase, typically with a more west to east jet stream, milder temperatures in the east. If we look here on the right, the negative phase of the NAO, we have a different situation entirely. With the negative phase of the NAO, we have a blocking high extending into Greenland, and sometimes this blocking high works its way northwestward into portions of eastern Canada and Hudson Bay. And what that does, we have a weaker jet stream, we have more of a meridional pattern. So we have a relatively, by the way, what's really interesting is we get a relatively weak 500 millibar high further south over the Azores, and a relatively weak 500 millibar low to the southeast of Iceland during the negative phase of the NAO. So this blocking high just takes over during negative NAOs. What that results in is this troughing of this dipping of the jet stream, or troughing along the U.S. East Coast, resulting in colder than normal temps for the east. So now you can kind of see why we would see more frozen precipitation up the eastern seaboard from the mid-Atlantic to New England during a situation where we have El Nino winter plus a negative NAO. Now, if we look at El Nino and negative NAO together, additionally on these graphics, we're showing temperature anomalies here on the left. You see the blue coloring indicating below normal temperatures. This actually occurred in the winter of 2009-2010. We saw higher than normal temperatures across Iceland extending into eastern Canada associated with that high latitude blocking the upper level ridge there. And we saw colder than normal temperatures over northwestern Canada right on down into the eastern U.S. If we look at the pressure patterns, this is very ideal here on the right for a cold and snowy situation on the east coast of the United States during winter. We have the southern storm track, which is very important, so we don't have these storms cutting up into the Appalachians and putting the whole east coast in the warm sector of these cyclones. We keep the low storm track, low pressures further south, keeping that same area, New England and the mid-Atlantic, in colder conditions. And again, then we have the ample moisture from that subtropical jet. Cold plus moisture, and you're in business. You have this strong upper level high, higher pressure or higher heights up between Greenland and the Hudson Bay area. So this is a really good situation for a stormy pattern. Storms moving from west to east from Southern California along the Gulf Coast. Sometimes these storms can actually move up the Gulf Coast. If you get this blocking high or negative NAO further west in a certain position, like right in here off the southern tip of Greenland, that will tend to block the movement of the East Coast winter storms. It'll block them from going right off the coast. This higher than normal heights north of the storm track, will keep the low pin closer to the coast. Here is the exceptional case of the NAO being negative during the winter of 2009-2010. It occurred during El Nino, and you can kind of just see how this is the NAO index going back to 1950, and you see some of the more key times where we had a negative NAO. Look how consistent, for example, the late 1970s winters were with this blue bar here dipping below the zero line, indicating a negative NAO. So these were the severe U.S. winters of the late 1970s. And since then, we have had the NAO drop negative. For example, in 85, it went negative pretty good. Also in the late 90s there, it went negative pretty good. And then we see this major drop off in the winter of 2009-2010. We had a major high latitude block. We had colder than normal weather beneath that block across the mid-Atlantic region, plus that very active subtropical jet stream with storm systems riding basically from west to east along the Gulf Coast and further south. So you get any of the overrunning moisture from these systems over the colder than normal temperatures associated with this strongly negative NAO, and you're in business for frozen precipitation. If you look at the North Atlantic Oscillation plus El Nino, these are the surface temperature anomalies for the 2009-2010 winter, courtesy of NOAA. All right, so let's just take a look at each of these. Let's just take a look at El Nino on the left. Let's take a look at the NAO in the middle. Let's take a look at the combination of a negative NAO plus El Nino on the right. All right, so simply an El Nino winter season. What does it promote? Cooler than normal temperatures, definitely from the desert southwest around the New Mexico area eastward to the mid-Atlantic. This light green shading here represents, you can see the scale here on the bottom, -1 to -1.5 degrees Celsius below normal here. Warmer than normal temperatures, the orange coloring, up across eastern Canada, Hudson Bay, right on into western Canada, typically in the Pacific Northwest. What happens if we look at just the NAO going negative? Look at this. Look how profound the influences of a negative NAO is on eastern U.S. temperatures. We went from a light green shading with just El Nino winter, and now we have negative NAO, and wow, we're talking 1.5 to 2 degrees Celsius below normal across a large chunk of the eastern U.S. during a negative NAO situation in the winter. And then look at this. Look at the higher than normal temperatures associated with that blocking ridge from western Greenland right on into eastern Canada. Now, what happens when we take a negative NAO plus El Nino and combine them? You still get the same signal here. Below normal temperatures from Texas, East Texas, right to the mid-Atlantic, to Virginia, and then higher than normal temperatures associated with the blocking still over the southwestern coast of Greenland into eastern Canada. So bottom line here is El Nino does favor cooler than normal temps across the South and Mid-Atlantic in the winter season, but this NAO influence is overwhelming right here, okay, by just looking at this data. This was the 2009-2010 winter season, and it's no surprise based on how strongly negative this NAO got that year. That's why it's so unusually cold across the eastern U.S. And then when you combine both the fact it was El Nino and a negative NAO that winter, boom, there you go. All right, now let's take a look at the storm tracks when we have a negative NAO plus El Nino combined. This was, again, the winter of 2009-2010, and wherever you see the brighter orange coloring or just even the medium coloring here, the orange, that indicates the main storm tracks, the cyclone frequency. So storms generally during the El Nino and negative NAO combined situation of the 2009-2010 winter season were extending right along the coast from the mid-Atlantic up just off the coast of New England. This was a hotspot for cyclone activity for the storm tracks. Do you notice it's not going back in and cutting inland up the Appalachian Mountains towards New York State, where the East Coast is in the warm sector? You're going to get southerly winds in that case. That happens a lot more during La Nina winter seasons. I thought this was a really cool graphic to show you. We're looking here, okay, let me explain this. This is courtesy of NOAA, the Baltimore, Washington, D.C. National Weather Service office. This shows seasons with above normal snowfall at Washington, D.C. since 1950. These are all the seasons right here on the right, to the right of the graph. So the big winner was 2009-2010 winter season, where Washington, D.C. recorded 56.1 inches of snow. And it goes all the way down 25 seasons to 73-74, where a D.C. area only saw 16.7 inches of snow. I want you to focus really this is all the winter seasons. This includes all the combinations of what you see here on the left. So in the upper left portion, we see a La Nina plus a positive NAO over here in the upper left. We see a El Nino and a positive NAO over here in the upper right. We see an El Nino and a negative NAO in the bottom right, and we see a La Nina and a negative NAO in the bottom left. Each of these triangles represent winter seasons. Now, these bigger triangles represent more significantly above normal winter seasons, right? So, if we look at where we have all these little diamonds, we notice in the bottom right-hand portion of this graphic, we have a lot more of these diamonds, right? That indicates we've had a lot more above normal seasonal snowfall when we have a combination of El Nino plus a negative NAO. So we looked at 7 winter seasons in this particular section of the graph with above normal snowfall in Washington, D.C. Only 3 winter seasons had above average snowfall when we have the El Nino plus the positive NAO. Again, I'm stressing the importance of the NAO, the North Atlantic Oscillation. Positive NAO, look at how limited the number of triangles are. If we look at the negative NAO plus El Nino, we have many more, all right? In La Nina, either the positive NAO or the negative NAO, there were a couple big storms with La Nina and a negative NAO. but there really weren't many big storms with La Nina and a positive NAO. So this NAO is huge. It's huge, huge, huge. Let's keep going. I'll break this down further into specific cities for the Northeast seasonal snowfall with the various combinations here shown. I'm going to focus in on really two columns in this graphic for these cities. Strong El Nino and a positive NAO, and strong El Nino and a negative NAO. These two, and then I'm going to compare them against the average over here on the right for a winter season for snow. What we glean from this is there's typically below average snowfall totals when you have a strong El Nino and a positive NAO. See, most of these cities from Boston right on down the line to Washington, D.C. Are running below the seasonal normal snowfall, which is over here on the far right, when you have a strong El Nino and a positive NAO. But when you change things around and have a strong El Nino and a negative NAO, for the majority of these cities, we see above average snowfall occurring. So that again proves our point that, in addition to El Nino, what's the NAO phase going to be for the particular winter? We look at southern seasonal snowfall totals, including you in Amarillo, Texas, you in Dallas, Fort Worth, you in Charlotte and Atlanta, all the way down to Oklahoma City, Raleigh, and Roanoke, Virginia. We looked at the similar columns here, strong El Nino and a positive NAO. Here's the averages on the right. So in this case, some of these cities actually finished above normal despite the positive NAO. And it's no surprise, really, because some of these cities are further west, away from the effects of the positive or the NAO, the North Atlantic Oscillation. For example, Dallas. But in general, I just wanted to show you, the differences. Raleigh, closer to the influence of the NAO in the eastern U.S. You're finishing slightly below normal with a strong El Nino and positive NAO, but you're finishing above normal with a strong El Nino and negative NAO. Roanoke, let's see how you fared. Below normal with a strong El Nino and positive NAO, and above normal, almost double the normal seasonal snowfall in Roanoke, Virginia, when you have a strong El Nino and a negative NAO. So again, it matters. So in summary, to end today's video, El Nino winter seasons typically result in above average snowfall across the eastern U.S., especially in the mid-Atlantic. And if you add a negative NAO to the equation, along with the El Nino, you get above average snowfall being much more likely to occur. And a great example of that is the 2009-10 winter season. And again, the NAO went really sharply negative and record territory negative in that particular winter season. So it is a little bit more of an extreme winter season to compare. But I just wanted to get the general idea across. Now, the NAO definitely plays a significant role during El Nino winters. El Nino typically favors a positive PNA pattern with colder temps and upper trough position over the eastern U.S. And again, not all El Nino winter seasons are ever going to be exactly alike. There's other things we have to consider besides just the NAO, which we've covered extensively in combination with El Nino. We have to look at other climate drivers or teleconnections, such as the strength of the stratospheric polar vortex. Will it be strong? Will it be weak? The strength of the El Nino is also an important consideration, with different outcomes have been displayed. A weak versus a moderate versus a strong versus a very strong El Nino. And the right balance of ample moisture from a stronger subtropical jet stream plus colder air moving in from the north with the polar front jet stream, that's the ideal setup you get for increased snowfall totals. And it really goes down to the storm track being further up the coast and offshore, vice cutting up inland across the Appalachians, or even back west towards the Midwest, like we see during La Nina winters. That's the big difference there. But again, I just wanted to delve into El Nino and snowfall during the winter season for the U.S. That's all I've got for now, everybody. Hope you enjoyed the video. And until next time, take care and God bless everyone.